Estamos en YouTube.
Sí. Ahí, entonces, esa es la cámara.
Esta es la segunda cámara.
Ya la persona está.
No sé de esta persona, pero esta cámara se puede mover. Hay la de la compu también. Y también hay la presentación directamente. Tac, vamos a ver. Tac. Esta es cámara 1, cámara 2. Esta es la de la compu. Pero hay como 30 segundos de cambio. Ahí estamos. ¿Ves? Tengo que arreglar el foco de esta.
Igual es.
Tac.
Y esa es la compu de Leandro.
Sí.
También funciona.
También funciona. Tac.
Wow. Hay que ver que solamente para saber, porque bueno, a veces el problema es.
¿Quién es ese lobo? ¿Cómo estás? Hola, ¿me escuchas? Hola, Hola, Eduardo. ¿Me olvidé?
¿Otro micrófono?
Sí. Tac. Me olvidé la contraseña del wifi. Ella la tenía, pero...
AP Casará 1,
Sí, esta es la red. Y el código...
Labo,
Tac, lo voy a anotar.
Labo.
LPC, todo minúsculo.
LPC.
1, 2, 3, 4, 5, 6.
Labo LPC.
Sí.
LABO.
Sí.
LABO. Labo.
Sí.
LPC. 1 a 6.
Ok, sí, sí.
Perfecto. Hay otra cosa, están haciendo una reunión al lado y están proyectando algo y no pueden bajar la pantalla. No saben cómo hacer.
Me hubiesen avisado que usaban la sala también.
Ah, pensaba que Denis es solamente una hora para la reunión de abajo. Muchas gracias.
Este queda abierto, ¿lo vas a usar el micrófono este?
No, creo que con los dos ya estamos bien.
Bueno, si no me pedís y te traigo. Porque queda abierto.
Puedes cambiar al otro mucho material si.
No. Todavía, ahora no. ¿Qué hora es? ¿No? ¿Dónde está la charla?
Ya está.
Mañana a las 14:30.
Pero de acá.
Tac. Tengo que... ¿Cómo hago esto? ¿Puedes cambiar el foco de la cámara y te digo si está bien o no? Más en la otra dirección. Ah, shit, qué pelotudo. Estoy mirando 30 segundos atrás. Tac. Si parece bien. Bájalo un poco. Cambia un poco el foco en una dirección. Oh, está bien. Está bien, gracias.
No, pero eso todavía no tan, ¿no? Esa cámara, eso se puede mejorar, ¿no?
Y acá, si se termina la función,
Sí. Este es...
tenés la cámara y...
Hay esta cámara acá. Y la cámara allá.
Sí, sí.
Hay la presentación en el centro y este es lo que yo estoy mandando a YouTube. Espero que se escuche algo.
Alguien te prueba, ¿no? que lo siga por YouTube y te va diciendo si se escucha.
Hola. Hola, ¿qué haces? Hola, ¿me ves? Ah, ya. Este libro es más sencillo. Lo siento por el tema del cambio de horario, es que se cambian un montón de cosas hasta el fin de totalmente no digitalizarte. Sí. Ahora, si quieres hacer una prueba, lo que hay en Skype es que si hay un plus abajo de la pantalla. ¿Ves? Hay algo. Sí, si lo pulsas, vas a tener la opción de compartir la pantalla. Sí. Ahora, ¿estás seguro que tienes la última versión de Skype? Bueno. A ver. Sí. Ya ves. No, nada. Yo me veo, estoy muy lindo, pero no te veo tú. No veo tu pantalla. Bueno, voy a colgar con el teléfono, voy a tomarte con la compu, ¿sí? Puede ser que es porque soy sobre un teléfono. No lo creo, pero bueno. Llamo de vuelta. Hola, ¿me escuchas?
Sí. Sí.
Bueno, ahora te voy a compartir mi pantalla. Voy abajo, pulso el plus y hago compartir pantalla.
Yo hago lo mismo. ¿Sí?
¿Ves mi pantalla ahora?
A ver, un segundito. Sí, a ver, te veo a vos. Bueno, yo a ver, voy a abrir el segundito, ¿eh?
Dale.
¿Ves algo?
Absolutamente nada.
Ok, un momentito. Un momentito. A ver. Skype.
Si miras mi pantalla, es acá, ¿ves? Donde hay mi cursor.
¿Dónde está Juan? ¿Qué cosa?
Mira la pantalla que te comparto. ¿Ves? Acá hay el plus. ¿Tac?
Sí.
Y
Sí.
tac.
Ok. Pero yo la toco también. Bueno, pero vos no ves mi pantalla.
Yo no veo tu pantalla. Esto es cierto.
Partager fenêtre, partager l'écran, démarrer.
Ahí,
Ahí te hay algo.
sí, está me pone que está esperando datos.
A ver,
Esperamos
permitir écran pantalla. A ver.
No toca nada, está por llegar.
No,
Imagínate,
yo te mandé antes los ficheros, eso no tiene nada que ver.
bueno, imagínate que todo el mundo está escuchando este sobre YouTube.
¿Ah, sí?
¿Quién no está viendo el YouTube? Nadie, no. Tranquilo, pobre.
Tengo 15.000 espectadores ahora.
Ah, no, entonces van a decir que yo soy nulo, ¿no?
Escucha,
No es que me peino.
no llegó nada. ¿Podés averiguar con alguien en el laboratorio que tiene una
Sí,
cuenta
voy a
Skype?
averiguar tranquilo, ¿te ves? Hasta mañana. Como que eso yo hablo mañana.
Sí, lo siento por la falla de comunicación otra vez.
Sí, murió un montón de cosas, etcétera, bueno, está bien.
Lo siento.
Bueno, chao, entonces buena suerte con él.
Chao,
¿no?
chao, gracias.
Chao.
Ya estará pasado para mañana.
Ah, ok.
Sí, lo que discutimos viernes a la noche y sábado. En todo este quilombo me olvidé de comunicarme directamente con él.
En el programa puse la clave para la conexión Wi-Fi y normalmente hay 30. Entonces no somos más de 30.
Voy a averiguar si se escucha algo con YouTube, porque estoy seguro que no se escucha nada.
Ahí enseñando los videos. ¿Qué? A ver. No, tarda en arrancar.
Si quieres que la presentación pase
Sí.
a YouTube, es mejor que pase a YouTube.
O...
Tienes que pasar
Y no estoy segura de si cuando lo copio andan los videos, porque ayer hice una prueba y sí, por más que están copiados todos el mismo archivo, yo los inserté desde
no,
hoy.
no pasa nada.
Que si no, no sale por YouTube.
Voy a pasar por la marca.
Ah, y se ve feo.
No sé si se van a ver bien.
Bueno, a ver, probemos. Yo lo tengo en probemos a ver si se ve. Sí. Bueno, acá.
Sí. Ahora, recta a la izquierda tienes.
Ay, perdón. ¿Esto ya se está viendo por todos lados?
Sí. ¿Quieres que apago?
No, no está bien, no pasa nada. No, para saber, no decir nada incorrecto. A ver si anda. Entonces, normalmente es este.
Eh ben ouais. Moi j'ai des profils,
Bon, ça commence.
Bueno. Non, ce qui commence mal déjà, c'est que toi, tu utilises Office. Ça, c'est mal.
Ce lipstick là, je
Attends, les mecs du Dipsy, ils veulent pas qu'on l'utilise. Skype, mais par contre, Office, il n'y a pas de problème.
Ben voilà.
Ok. Ok. Voilà.
Tu veux que je dise?
C'est la fin du monde.
Bon, mais qu'est-ce qui se passe? Ça ne marche ou pas?
Ouais. Attends. Je crois qu'il est en train de télécharger Office. Bon, utilise ta machine, on va pas tout révolutionner
Utilise ma
maintenant.
machine. Voilà.
On va pas tout révolutionner maintenant. ¿Todo bien? Tu resto, c'était bien? Tu resto, c'était bien?
C'était pas survenir, c'était le 6.
Muy bien. Hola, Ricardo. ¿Cómo va? ¿Cómo va?
Todo
Está
tranquilo.
la clave para conectarse. No, entonces, no conectamos. Ah, me puede mandar un mensaje ahorita. Thomas,
Oui.
au lieu de j'ai allongé, si je dis j'ai élancé pour traduire Slender Jet, ça va? Ou ça va pas? C'est mieux allongé.
Je pense que oui, mais ni l'un ni l'autre ne me parle.
Non, mais c'est en fait un révieweur qui nous a suggéré d'utiliser Slender Jet. Donc maintenant je me pose la question par rapport au terme en français. Mais bon, ça te dit que c'est un G qui est allongé.
Oui, oui,
Et
oui.
allongé, c'est mieux.
Oh, elle est lancée, enfin sur les bords, avec un rapport d'aspect élevé.
Oui, mais c'est ça qu'il n'a pas voulu dire parce qu'il dit que l'élevé c'est 100 et que nous on est à 10. Bon, c'est une question.
Con el Linux creo que tenía ese problema que no avanzaba lo que está en la pantalla ya acá. Por eso que chequear.
¿Cómo?
No tiene. ¿Era? Eso. Ahora sí. Ok. Entonces sí estamos. Puedes cambiar. Ahora no, pero mira.
Sí.
Mira, así.
Hola.
Eso es muy largo. ¿Qué hace eso?
¿Cómo?
¿Qué hace eso?
No tengo idea. Es cierto que... Ah, puede ser porque no tienes solamente una pantalla.
Así que hasta aquí. Está bien. Son las pequeñas partes de Linux.
Che, muchas gracias.
disculpa por las idas y vueltas.
No, está bien, está bien.
Sé que vos estabas hablando con el medio,
Bueno,
yo tengo ahí un adaptador.
¿quieres solo con tu compu
Sí,
o
me
pasarla
parece.
en YouTube?
No, no.
Estamos en YouTube ahora.
Sí, di la página web. ¿Cómo es eso?
Con este, mira, sí, tengo esta aplicación donde yo puedo, acá yo paso la pantalla que
buenísimo.
quiero, hay esta webcam aquí,
Sí,
hay la otra acá,
claro.
voy a tener que
Está muy
ponerla
bueno.
sí, y es libre, es
Wow.
Open Broadcast Software,
Ok.
onda
Bien.
no pago. Probé con aplicaciones que recomienda YouTube, que
Ajá.
tienes que pagar para tener
Sí, claro, claro.
Acá
Y-
tienes todo lo que necesitas por nada.
OBS, ok.
Bueno, te mando el enlace si quieres.
Dale, sí, cualquier cosa. Con esto lo quería enchufar porque me di cuenta que estaba
Sí, hay.
descargada y por otro lado tengo por acá. Buenísimo, gracias.
Una charla, hola.
Ahora, ¿qué haces?
Voy a poner un logo, hola.
¿Todo bien?
Todo bien. Puedo poner mi computadora después, ¿no?
Sí, ¿quieres probar? Pero el cable que llega solamente hasta aquí.
No, sí, ahora me acerco.
Sí.
No sé si. Esto creo que. No, sí. Bueno, entonces venís. Nosotros tenemos seminario del departamento los jueves.
Los jueves, muy bien.
Yo creo que el jueves que viene ya debe estar, o sea, este jueves ya debe estar tomado.
Sí, lo espero.
Pero, claro.
Espero que lo organizan los seminarios
Por
como
eso,
se organizan.
por eso. No, es alguien más que los organiza, por eso. Pero te propongo y
Sí,
obviamente.
bueno.
¿Te parece?
Me parece.
Es los jueves a las 2 de la tarde.
Perfecto. Bárbaro.
¿Quién los organiza?
Los organiza el departamento de física. Y los organizadores concretos van cambiando el tiempo. Ahora hubo un cambio de dirección, por tanto se cambiaron los secretarios académicos, pero también los que organizaban los coloquios. Ahora hay dos personas en condiciones, una es Augusto Roca y otra persona que trabaja no, porque Augusto trabaja en cuántica. Y después está Luis Morelli, porque él hace algo rayanamente cercano a microfluídica porque trabaja con biólogos. Pero ya te digo, va fluctuando.
¿Los expositores son todos desastres?
No, al contrario, se busca que no pase eso.
Yo estoy interesada, pero...
Sí, decime y te... Decime y te...
Lo que viste no se conoce a veces, lo que se está
Sí.
Bueno, más o menos.
¿Vos sos el primero?
Sí, es el programa. Pero hasta donde había visto... Pues, ¿es eso?
Sí.
Prometo entregar a tiempo. Entonces vamos a sacar la
Razón,
wifi.
ya estamos tarde, ¿eh?
Ya estamos.
Ah, no.
Vamos a apagar el mail. Testing.
Después de entrar en la canción que se llama Enviar mi amor.
J'aime bien ta appli l'espagnol, t'as appris l'argentin.
Ah bah ouais.
Directement, voilà.
Zéro classe d'espagnol. Ninguna clase.
A ver. Ok.
Bueno, este es mi compu, si quieres cambiar esa carta.
Ah, genial. Ah, bien, a ver, déjame ver si pongo las cosas donde debería. Mi máquina está lenta.
Normalmente no. Oh, super. ¿Quieres probar el tuyo?
Sí, sí.
Sí, déjame, todo eso porque no.
Ese soy yo, bueno. Sí. Chef, el gran chef.
Ahora. ¿Qué haces? Te escucho muy mal. No. No, igual te tuve con el teléfono porque estamos por empezar acá. Bueno. Fíjate cuando está la cosa que hace acá y tú me de vuelta. Chao. ¿Qué pasa?
Estamos todos con compus distintas, ¿no?
Sí.
Bueno, yo mis cosas no tiene software libre, nada, tengo que usar la mía.
Ah, sí. Pero lo bueno es que trajo este multiconector que aparentemente puede servir todas.
¿Ah, sí?
Sí. Tiene varias, no tiene 3 conectadas ahí o 2 conectadas.
Ah.
Y funciona bien.
Ouais, on était tout seul. Ouais, ¿te reprochó algo? Te dijo que no. Si no, le digo con sonrisa, bueno. Porque igual si estamos solos y cosas, que importa en qué habitación nos metemos. Está bien que estaba reservada esta. Bueno, tú tampoco.
YouTube.
¿Qué digo con los mails, Pablo? No te llegó ninguno.
No.
¿Y cómo puede ser?
Es
¿Qué
muy raro.
mal el servidor de Fiuba? ¿Qué es lo que pasa?
O el nuestro, la verdad que no sé.
No, pero los demás, porque
No,
tengo
pero
un par de
estamos
mails,
todos
lo tengo
centrados.
grabado en enviados y
Sí.
él verificó en el mail y no lo tiene
Lo que hay que
recibido.
hacer es un grupo común.
Probablemente
puede ser
se lo va.
Y en este hay también tienes un archivo de pasar por el mailings de verdad y no solamente la lista que está en
¿Cómo? ¿Pablo Minini? No, y fue va.
Si la gente puede ver igualmente.
¿Qué hay sin
Siempre
necesidad
hablan
de
de eso.
recibir el mail?
No, je pense
Quel
que
direction
tema, il y a
sta
une
sperando che
programme
Sí.
di
Bueno,
Ahí
eso
sí,
vamos a
pasa
ver
la
si
Bueno,
es
bueno,
una volvés, pero debe ser una volvés.
lo que tenemos con el laboratorio.
Sí, ya sé.
El IA Group es
Hay que crear el grupo y vas poniendo, agregar las direcciones de mail al grupo.
Exactamente.
eso está
Y además cada uno tiene que
Aceptar.
aceptarlo.
Así que si no acepta, es que no llegó.
Claro.
Obliga a la persona.
Y una vez que está, es casi seguro que después siempre va a llegar.
Claro.
Bueno, haremos eso la próxima.
Bueno, está bueno. Sí, Pablo, creo que lo que iba a hacer Pablo era fijarse, yo hablé ahora un poquito a la mañana y lo que me dijo es que me voy a fijar a la gente de compu a ver si por alguna razón
No,
esos
también
mails se
la otra
están
causa
filtrando.
puede ser el de Fiuba, que figure
Sí,
como
sí.
enviado y
Claro.
que no, después no llegue. Pero bueno, está bueno saber dónde,
Sí.
dónde se quedó trabado.
Estás justamente al frente del canal.
Ah, sí.
¿Yo estoy
Sí.
tapando?
No sé si se ve o va a ser difícil de ver algo.
Está bien.
Igual,
Sí, es.
no tenía mucha esperanza.
No,
verdaderamente. Pues hay que si hacemos algo.
Ujú.
Se puede copiar este a mi compu y yo lo paso a descargar al mismo tiempo.
Tiene muchas movies. Y aparte es Keynote, ni siquiera es Power.
Yo lo paso a los movies,
Claro.
lo exportas a PDF
Ajá.
y paso al menos los tags al mismo tiempo.
Ah, a ver, dale.
Bueno,
Entonces. Ah, sí, tengo todo. Entonces que voy a cortar cosas. Vamos a hacer thank you. Vamos a hacer lights que no sirven de nada. File. Listo. Y ahora sí. File. Export to PDF. PDF. Next. Bien. Te respira en la nuca.
Lo que voy a hacer es que yo voy a cortar Skype porque nadie que está hablando por Skype esta mañana.
Bien. Ahora paso una llave. Entonces, por ahora. Y te lo paso.
lo que hay que enchufar y desenchufar para que salga la pantalla ¿Y dónde está? ¿Cuál es el video?
¿Para qué?
Cuando tenga que conectar mi compu.
Sí.
Con este.
Sí.
Y el otro, nunca
Te lo mando por correo porque mi llave no anda, no sé por qué.
¿Vale?
La Clay no quiere. Pero te lo mando por mail, sí. Acá.
¿Querés que probemos? A ver si conectamos con otra.
Dale.
Pero yo no tengo película, nada, así que...
¿Querés? ¿Sabés cuál es la wifi de acá?
Sí.
Nada más.
Empezar a uno.
Empezar a uno, sí.
Labo. LPC.
Ah, perdón. Vuelta. No.
Velocidades del
Saúl.
mundo.
Sí, sí.
¿Cómo estás?
Hola.
Hola, ¿qué tal?
¿Cómo va? Entonces me decías, el Labo,
LPC.
LPC.
1, 2, 3, 4, 5, 6.
Ok. Esto debería estar bien y así te lo mando.
Bárbaro.
Oh, Guillermo, ¿cómo estás?
Cuando Titi la dejo ya conectado acá, me parece.
¿Escuchamos bien? Bien.
Te desconecto entonces.
Sí, porque
Pues total ya igual la voy a dejar por acá,
A la derecha. 12:30. Ah, qué lindo teléfono.
la calidad de la imagen no está buena en YouTube.
¿No?
No,
¿Dice él?
es que me dice por eso me llama en Skype para mencionar la calidad de la
Sí,
imagen.
lo mejor es comprar un pasaje y venir.
Cuidado que se escucha y el micrófono acá.
Bueno, ya te las mandé.
Este,
Va a tardar en llegarte porque era más o menos pesado. Pero
Empezar no sé, Google
12 megas, pero.
12 mega.
Ajá. No sé por qué, porque. Oh. ¿Todo bien?
On va commencer. Je vais dire quelques petits mots.
Tu peux connecter une machine?
Voilà, celle-là. On a son adaptateur, on a son.
Où est-ce qu'il est ton.
Ah là, il est là. Ah, pas de problème technique.
Ouais, la qualité des vidéos sur YouTube est naze. Je pense que le son va pas être terrible non plus. Au moins les gens ici pourront écouter. T'as un micro? Peut-être qu'avec le
Je sais
micro.
pas par où commencer en fait. J'ai préparé d'autres trucs avant, mais je crois qu'on va.
J'ai changé tout le programme en fait. Hein.
Là, en fait, j'ai pas eu le temps de traduire le premier. T'as pas eu le temps de changer tout le programme?
Ah, je dis j'ai changé tout le programme.
Ah oui.
J'ai invité des amis.
Ah oui, vous pouvez venir dès le voir sur YouTube.
J'ai 4 chimistes qui vont passer à 17h.
So chairman is Amiro, the Amiro chairman.
Pero así es lo listo.
Et moi,
Señoras y señores, vamos a empezar.
¿Perdón? Más o menos. Ya.
Hola, hola.
mes parents peuvent nous voir, c'est ça?
Même elle t'écoute.
Hola, buenos días.
Amanda?
Hola, buenos días.
Ah oui, en fait, il faut le micro pour. On peut parler sur le micro.
Tu peux parler sans le micro parce que de toute façon, je pense que le son n'est pas terrible.
Donc, so buenos días. So, I'm going to speak in English, okay? Because there is some people that are not speaking Spanish, and some Argentinians that are not speaking French, I think. So just before the beginning of the days of the presentations, I will just show you a few slides about the collaboration between France and Argentina in the LIA. Okay, so LIA means International Labs, and we have some French labs that are part of this LIA. So there is the FAST and the LIMSI. It's two labs that are in Paris, in Orsay, so it's close to Paris. And PMMH, downtown Paris. PPRIM, it's a lab in Poitiers. And there is also one lab in Rennes and one lab in Lyon. Okay? So that's for the French side. And for the Argentinian side, there is El Grupo de Medios Porosos, LFD, that are both à la Facultad de Ingeniería, El Grupo Hidráulica, y Exactas, y el Instituto de Física Aplicada de San Luis. Y so, the idea of this group of labs is to have a joint effort to do research on fluid dynamics. Each side gives some things to the collaboration, bring some things to the collaboration. Okay. So during the days, you will see that there is activities about granular materials, with some simulation in France and some experiments in Argentina. There is things about the interaction between fluid and structures, turbulence, waves on surface. So it's a broad collaboration on fluid dynamics. Just to some data about the collaboration. So here, for example, it's for 1 year, 2 years ago. So here on this, you can see you have the number of missions that have been done. Okay. So here you have the first row, financiation, es las estrellas that the LIA paid. Okay, so you have something like 5 missions from France to Argentina and 7 in the other direction. So you have each year you have something like 10 missions in collaboration. But you have also some parts that have that are not financed by the area, and that's 7 additional missions. This you can see that here it's the type of extra money we can have to do this type of mission. So we have some of you have been Professor Invitado or have received a grant for to do la Cotutela and Francia or in Argentina. So each year, that's typically what the LIA is doing. This is more or less the same for last year, and I guess that this will be the case for this year. Here you can see it's the number of publications made by the LIA. So you can see that we start 6 years ago with 2 to 3 articles per year, and now this year there is 10 co-publications in the lab. So I'm not going to go through all the publications. You have some information in the on the poster. We have also organized some meetings, some seminarios, joint seminar, cursos, so 13 cursos y taller, okay, that have been organized by some researcher in the lab, in the area. So that's a little bit the program for these 2 days. So 21 talks about some research activities in the lab, made in the lab in collaboration. There is also Mesa Redonda, el martes a las 11. So everybody is welcome to this Mesa Redonda. Redonda. On Wednesday there is between the 2 visits. So Wednesday we are going to visit LFD and El Grupo de Medios Porosos, and in between we will have a joint un almuerzo común. Empanadas para todos. No más de 3 empanadas per persona. So before the first talk, so everything is going to be all right because Jesus is with us. And we can see here that Jesus is able to, from water, to make some wine. So it's the real Jesus.
Where did you get that?
From Fridos. Ouais.
For everyone, there is the possibility to have lunch at when we stop in a restaurant and it's 1 block away from here. There is a executive menu for 144 pesos that is everything. I know it's not very cheap, but we have gone around looking for good prices and a good meal, and that seems quite okay. So those who are interested, I will beg you to tell me who will come so that I can tell the restaurant how many we are, so that they plan everything and we can not have delays when we have lunch, so that we all back on time. The coffee break, you could please tell me if you're planning to come or not. Please, I will be available.
Sur la convertir l'image, en tout cas les gens vont pouvoir tout travers la caméra.
Okay, so the chairman is going to chair.
Yeah, so
We're good.
okay, so maybe just before starting with the program, today I would like to say again something that I always say. The Mesa Redonda, the round table, is for everyone. So I mean, the executive committee with Irene, Guillermo, and myself, we've already started discussing, and we'll discuss with the people from CNRS. But it would be good that everyone participates to the roundtable so that we can hear other voices than the usual. Okay, so let's start with today's program. It's Pablo Covelli from Exactas who will be starting. He will talk about water weights.
Okay. Thanks. Good morning to everyone. Thanks for the organizer for arranging this slot of time, which I couldn't do any other. So thank you very much for that. And let me just begin, as we are as a group, as we are the newcomers to the LIA. Let me just say a few words quickly about our group. I represent the group of Astrophysical Flows, which is located at the Faculty of Natural and Exact Sciences. You won't find it there. It is composed of the 5 permanent members that are on the top row there, and the number varies, but we are like between 7 and 10 PhD and postdoc students, and typically 4 undergraduate students, which are doing either their master thesis or their last experimental subject of the career. And we are interested basically in numerics, in observational tools. The group develops its own numerical codes, and we have our own clusters to run them on. And we recently started a lab. We have these experimental techniques available now, and these capabilities. I mentioned this just to maybe stimulate some new collaborations within the LIA. Those are things that I will discuss later, and this is a much broader list of collaborators, long-standing collaborations of the group. So let me, after this very brief presentation, let me just start with with what is promised in the program. So I will talk today about laboratory experiments in water waves, which were carried within the collaboration. And basically, those the works that I will discuss today are made in collaboration with EMMH, basically with Philippe Duchamp there at the SPCI. And so, very briefly, the contents of my talk will be the space-time resolved measurements of the free surface in gravity capillary wave fields, how to measure gravity capillary wave turbulence, and how we develop together a new tool to measure this Broadband spectrum, and the conclusions and perspectives of our work. So the story begins with trying to measure this, which is the interaction of waves with a pin vortex. Okay, and this is a 2D problem, and so we need a 2D tool to measure this. So we came up with this a few years ago already. We came up with this fringe projection profilometry technique, in which we project a structured pattern, which can be just lines or dots or whatever, but we know it, and we interpose an object, and that deforms the fringe pattern. And if we compare both, then what we can do is we can go back to the 3D structure of the deformation. So this can be applied to water waves, and this is what we do. We have a tank like this, a projector, and a fast camera, and then we project that sort of pattern, which has a profile like that in intensity. And so this is what it gives. If I just add a dye to water, I get this. So you see the fringes there. This is just to show you how it works. And then I'm going to shake the surface with a paddle, this is what the camera sees, and in real time you get the result of that. So this is over 1 million points, and it's only limited to the velocity of your camera. So if you have a 1000, which is a lot, frame per second camera, you can get this sort of reconstruction. Okay. Other typical results that we are able to get are the impact of the drop, or vortex like that, the emission of spiral waves. So ever since the beginning of this technique in 2009, there's been a lot of communications involving this technique. The references on the technique are there, but most of the results on high impact journals are there, and we applied this to fields in which the deformation is kind of mild originally. But what happens if one wants to study a field such as this, which mimics, or one can say, is similar to the turbulence in the ocean? Okay, so you see this picture and you see big waves, and you see also shorter waves. So this is very broadband, it's 2D, it's very dynamic. So how to measure this? So for a moment we can forget about the waves, and all we can think of is trying to develop a technique in which you have a certain roughness of your surface. Your surface is static, so you don't have to worry about the dynamics, and you just want to measure that. So in wave turbulence, in this regime in which the waves are highly interacting between themselves and it is non-linear, what we can see is that we have a random height surface. It's kind of a rough surface with an isotropic power spectrum, because that is what we expect when we study wave turbulence. And so we model it like that, and we have a random phase field which is uniformly distributed there, and so our imaginary rough surface would be something like that. So if we try to rebuild this rough surface with the technique that I've shown you, with the first technique that we developed, we get this reconstruction, which is very bad. You can see that because you don't get the fine structure which is in the original. So in the last 2 years, we developed a new technique which we term EMDP, empirical mode decomposition profilometry, and which is much better in results. But this is just naked eye comparison. So you can do much better than that. For example, we can calculate the spectra in space for the 3 of them: the original, the FTP reconstruction, and the MDP. And this is what you get. So the maybe if I have a pointer. So this is the spectra in terms of K, okay? And the black dots that are hidden by the blue line are the original. The blue line is the MDP reconstruction, and the FTP is our original technique, which doesn't work for this kind of highly irregular field. Okay? So we developed this new technique, and the other thing that we did for testing how good the reconstruction was is the following. You can think that this original surface is, as I said before, is randomly distributed. So if it is randomly distributed, you can think of that as a data set that comes from a random distribution, from a random population. And so you can run a test, a Kolmogorov, which is called a Kolmogorov-Smirnov test, in which you test for this and this distribution to be something that you pick randomly out of a broader original population. So what is the probability of having picked this casually from this one? And what is the probability of having picked this over this? And what you get from a Kolmogorov-Smirnov test is just a number which tells you, or decision, which tells you if these two sets are similar statistically, and if these two sets are similarly statistically or not. So what we get is that with 0.98 p-value, which is very high, we cannot discard the hypothesis of these two being drawn from the same distribution. Whereas for this one and this one, the test rejects the hypothesis. So you can tell statistically that this and this are different. So it's not only the naked eye, you can say something statistically about the data sets. So we developed these new techniques. This has been published a few months ago. And this is good because we get something that spectrally reconstructs in a correct way our surface deformation, but also statistically. Okay, it respects the original statistics. If your original field was Gaussian, then you will get something that is Gaussian with the same parameters. Okay? And this is very important for waterway turbulence because most predictions are obtained in terms of the distribution of statistics. Okay? So I pass on to the experiments themselves. This is what we call waterway turbulence. As I told you, you can think of this as many waves interacting non-linearly. And so, just as a brief reminder of the wave turbulence predictions, maybe I can stop here for a second and just say that for hydrodynamic turbulence, you have predictions that come from Kolmogorov spectrum, and those come from dimensional analysis. Basically, there is no closed form solution for hydrodynamic turbulence. Whereas for wave turbulence, this interaction between waves instead of vortices, you get full results, okay, closed results. And so you get for gravity waves, for example, and spectra in omega such as this, and in K such as this. And for capillary waves, we have both, right? But for capillary waves, you have something like this, which is quite different, and something like this in K. So we are up to the search of that. So you've seen already our tank. So what we do is with the paddle that I've shown, we agitate this, and I will tell you how. So what we do is we keep the working liquid, it is water, fixed. The height at rest is fixed at 5 centimeters. We have the base inside, which is also fixed. And then we make your paddles, their geometry, and how much they are immersed, that is fixed. What we explore is two frequency forcing ranges in which we put a random noise, okay, that goes between 0, so it is one pass. It goes between 0 and 4 Hz, and another regime in which the excitation goes between 0 and 1.5 Hz. And for both frequency ranges considered, we oscillate these paddles with an amplitude that varies between 1 and 30 millimeters. Okay, so and we studied with this the 3D, the full 3D, K and omega spectrum. So this is the experiment running. Maybe it starts. Those of you who will visit the lab tomorrow will see this live, but otherwise this is what you get typically for something that mimics the ocean state, and this is what you get when you measure it with our technique. Okay, this is filmed at 2050 Hertz, and this is the deformation of the crystal. You get this, for example, these dimples there, those are bubbles. When they explode, they emit, and you can see them with the technique. It's very accurate. So typically, our results for the two regimes can be set up like this. So between 0 and 5 Hz and between 0 and 1.5, and you see the differences there. And the PDFs of the height distributions are already different there. You have long and heavy tails there, which you don't have in the mild regime. So if we Fourier transform this in K and omega, we get a spectra such as this. And you see that blue corresponds to low energy and red corresponds to high energy. So you see all the energy is along this line, and this line corresponds to the linear wave relation, dispersion relation, sorry. For the mild excitation, you see that we get an isotropy there. This is a ring of energy. So if you will, this is just a cut over this. Okay? And for the higher excitation, for the high forcing, you get something like this, which are well known in oceanography. Those are called bound modes. And so you get not only one dispersion relation, but several. And that is easily explained by the fact that when you get high interaction, high nonlinear interaction, you have one wave, one smaller wave, which travels like onto a larger wave. So you get this dispersion relation, which has many branches. If we do this again for the high forcing again, we always stay at the linear dispersion relation, but we have this broadening which has been predicted within the theory, and we always have isotropy. And so going back to the comparison for the spectra between this and the experimental results and the theoretical predictions, we get a -4, which is predicted by the theory. And back there we get with respect to the whole, so I don't find it there. It's there. So those are for the two regimes, and if we now vary the injected power, we can do that in our paddles, then we get relations such as this, which are very well predicted within the theory. And so I will just go briefly into new results. This manuscript has been recently submitted. If you plot the energy spectra, okay, for different times, and this is the energy spectra in K, so you have a K vector of color, and you put it there, and then you put the next one next to the first one, you get things like this, which if you look at them in detail, look like flames, right? So in turbulence in general, the transmission of energy between one scale and the next one is supposed to be done instantaneously. There is no time for the energy to be transferred from one scale to the other. Okay? What we see here is something quite different. It's the fact that from time to time you have accumulation here at the lower K, and then you have release. You have these planes. Okay? This has been predicted and observed numerically, but never before experimentally, and this is the first evidence of this behavior. And this behavior is similar, at least theoretically, to what is called avalanche dynamics. Okay, when you have a pile of sand, and then from time to time, when you pile up the sand, from time to time there will be an avalanche, which will draw the system into equilibrium again. So this is something similar in the sense that you put the energy in the higher K, in the lower case, higher lambda modes, and for a time it absorbs the energy and it only stays there at those scales, and then after a time, which we study in this paper, after a time it releases the energy to the rest of the system. So these are two views of two different dynamic scenarios in which the system is holding energy and which the system is releasing the energy. And okay, in my screen those are much more different than depicted there in color, but so these are new results, and this speaks of, as I was saying, of an avalanche dynamics. And in the paper we describe this and model this in terms of what is called self-organized criticality. So this is a much broader model for dynamical systems, and it fits well with our data. So to conclude, I basically show you some results on water wave turbulence that were done partially in France and partially in Buenos Aires, and we get particular conclusions there that I stressed out in the presentation. I just want to thank you very much, and if you have questions, I'll be glad to answer.
What is the advantage of using stripes?
No, there is no advantage. For me, it's just a presentation, because otherwise the pattern that I would have to show is just very dense dots, and you won't see anything. You would see something like gray image in the presentation, and so I use stripes just for the presentation. But it can be any structure pattern. If you notice the pattern beforehand, then it's okay.
It's the size of the pattern that gives the resolution.
That's a good question. With the original, let me just show you this, and it will become clear. With the original method, which is the FTP, that only works for mild deformation, that is for linear waves, if you want. Here it is marked is the K0, so the K naught there is the wave number corresponding to what you project. Okay, so you are good up to less than K0. With our method, with the method that I've shown for every image in this presentation for wave turbulence, we are playing with the blue one. So with the blue one, we go much deeper than that. So if you project something which is a millimeter, you can go up to half a millimeter and still be within the precision that you search. Yeah, but it's been an effort to develop this technique because standard FTP does not work for wave turbulence. It will give you something like bias, and you would say, okay, I'm not measuring what the theory predicts, but it's because of your filter. It's because of your technique. Yeah. No. Well, EMDP, as it is, our EMDP is based on EMD, and EMD was originally based on one transform, but one transform is the worst. And what we do is another thing that one suggested that works very, very well, and it's called direct quadrature. And this is, but let me just stress out that this is just for the analysis of the original images. once you get the height field or the velocity fields, then your analysis is via Fourier transform as a standard with windows and everything.
What is the difference in computational cost?
It's almost the same because we run these codes all in parallel in those clusters that I've shown. We have a cluster that is just for data analysis, and so it's almost the same. The only thing with EMDP is that you need some initialization, and that can take, like, I don't know, the same as for an analysis of termed images, but after you pay that price, it's okay. So for every image it's the same, but you have an initialization that is not there for everything. So I would say it's the same plus 30 minutes or so for 5 gigabytes of data.
Questions? Thanks again.
Thanks.
Okay, so next talk will be given by Maria Alejandra Aguirre. Yeah, and it will be on the granular approach to an aperture.
Well, I have done this work in collaboration with an engineering student, and with Jean-Christophe Seminar from the École Normale Supérieure de Lyon. And I will talk about the influence of the packing fraction on the flow rate of the discharge of granular material through an aperture. So first, maybe you remember what we're expecting to see. If we had a column of fluids, then we will expect that the flow rate will diminish as the discharge process through an aperture takes place. And this is because the flow rate is related to the pressure in the outlet plane, and then this is related to the height of the column of liquids. But in the case of granular material, what we observe is that the flow rate is constant, and this has been wrongly led to the idea that this is related to the fact that the pressure is constant in the outlet plane. We have done some previous experiments, which I will not have here in this presentation, where we found that this relation is just by chance, but actually even if pressure is constant and flow rate is constant, they are not related in the case of granular materials. Actually, we can do experiments where we can change the pressure and the flow rate and remain constant. So the flow rate, as I said, during the discharge of a column of grains is constant. It is independent of the height of the system, and actually, well, it is the mass flow rate is related to the packing fraction, the velocity at which the grains leave the system, and to the size of the outlet. In the case of a gravity-driven system, then the velocity will be related to gravity, and it is assumed that there's this kind of model. It's called the arch-free free-fall model, where it is assumed that at the outlet there's like a kind of an arch, and grains are kind of free-falling from this arch. So they start with let's see here. They start like with zero velocity here, and then they do a free fall, and they get accelerated by gravity. And this height, where the free fall occurs, it is assumed that it's related to the size or the length of the aperture. So we get this kind of velocity related also to the it's just like a free fall. Then we have that the size of the outlet is related to the length, or a characteristic length of the outlet, and actually it will be a little bit less than the real aperture. A is the aperture, is the length or the diameter, or if it's a 2D system, it's just the length, and it will be a little bit less. You can see here maybe there are some boundaries effects, and you can see that the real aperture it's a little bit less than the real one, just by some KD factor with D, where D is the diameter of the characteristic size of the grains. So taking this into consideration, if we have, for example, a circular aperture in a 3D system, then we will have that the size of the outlet will be proportional to the square of this effective aperture, and then we will have like this scaling law for the flow rate, which scales with the effective aperture to an exponent 5.5. And in the case that we have just a vertical 2D cell, then we will have that the size of the aperture is proportional to the effective size, and we will have an exponent 3/2. So what we're interested in is that we know pressure is not controlling the granular flow rate. We know velocity, of course, is controlling the granular flow rate, but we also have in that expression the packing fraction. So we wanted to know how the packing fraction was, or variations in the packing fractions were influencing or modifying the flow rate, and especially if there was uncoupling between the packing fraction and the velocity with which the grains leave the system. Usually, gravity-driven discharge are always, but most of the experiments are done with a kind of a constant packing fraction, because all the grains get packed near the bottom, and you get like a dense packed system. So, of course, if this coupling exists, we want to know if this Bernoulli scaling still holds. So, as I said before, in vertical systems, it's a little bit hard to modify the initial packing fraction. There's experiments work that has been done. But okay, we want just to make things a little bit more simple, and we were also working in a 2D system that it's a horizontal system. So what we do was to put the grains in a horizontal configuration, in a 2D horizontal configuration, and we instead of using gravity to drive the system through the hole, we use a conveyor belt, which we can control, and we get a constant velocity. So in that case, as in previous publications, we have found that the number of grains that get out of the system, that is the flow rate, is proportional to the packing fraction C, to the velocity of the grains near the outlet, and to an effective aperture, as I said before. A is the size of the aperture, and D is the characteristic size of the grains. So the experimental setup is like this. We have a conveyor belt, we have a confining frame on top, which has an aperture. And this aperture, we want to be sure we have a continuous flow, so it's about 10 times the diameter, the characteristic size of the grains inside, which are the granular material we use are rings with an external diameter of 4 millimeters. We did experiments changing for different values of the velocity of the conveyor belt, and of course with different initial packing fraction, which I will talk a little bit later. So we use here several velocity values, and what we do is we start the conveyor belt, we let the conveyor belt go at constant velocity, of course, and we let the conveyor belt run for around a tenth of a second, and then we stop it and we take an image, and so on till the whole confining frame or container is emptied. So the initial packing fraction, it's set in the following way. We have a fixed number of grains of about 300, 400, and what we do, we place them inside. The confining frame. Here we have the confining frame, which is the outlet part. Here we have the aperture of size A, and we have this width of the confining frame, which is W, which I will talk about at the end, so I will mention it here. And then we put all the grains with the highest packing fraction, so they are all together, and this means that they occupy a length in the confining frames of about 6.5 centimeters. Then what we do are some other experiments where the initial condition is we have the same amount of grains, but they are placed in a wider, a larger area. And then we have done we have done experiments with 4 values of the packing fraction, of the initial packing fraction. So with this initial, once we prepare the systems, we begin the discharge of the granular material, and what we measure is the packing fraction, that we measure it near the exit, and we analyze the evolution during the whole discharge of the packing fraction measured in this red dotted area, which is near the outlet. It is of the side of the length of the aperture, and it's about 2 diameters of the grains in width. And then, of course, we need to analyze the flow rate. So we measure the number of discs that get out of the system as a function of time. So what we obtain is the following. For initially high packed systems, that is dense systems, what we found is the evolution of the number of these as a function of the time of the discharge process. It's linear in these cases, and that means that the flow rate then is constant in this case, which of course we have previously observed, has been previously observed, and is consistent with what I have talked before about granular flows be discharged at a constant flow rate. But if we start with initially low packed systems, then we have this type of loose systems, and what we observe is that first the grains get packed against the downstream wall, and then they reach the asymptotic value, and then just they are always getting out of the system. So what we observe for the behavior of the number of things flowing out of the system is that we have a non-linear behavior, and of course that will lead to a non-linear behavior in the flow rate. So as for the packing fraction measured in the zone where we are interested, here I have some snapshots. We can see what I mentioned before. First, we have that the system is getting packed downstream until it reaches an asymptotic value. Here we have the packing fraction during the discharge process for different, for different initial packing fractions. What we see is that, we see that always the system reaches it is getting, as I said before, piling against the downstream wall. Still, in all cases, it reaches an asymptotic value. So what happens if for a given initial packing fraction we change velocity? Then what we have is that for lower velocities, of course, we need more time to reach this asymptotic value. So as in this case, the only time scale is introduced by the velocity of the conveyor belt. We can translate these times to the length that the conveyor belt is displacing, so we can change times to the distance traveled by the conveyor belt. And in those cases, we can make, if we plot the packing fraction as a function of this displacement of the belt, then independently of the velocity, we have a collapse of all the curves. And we see that the asymptotic value that is achieved is a little bit less than the maximum that can be achieved in this type of system, that is for this, which is of 0.82, which is the one for a random closed packing. Then also near the outlet, we measure the velocity that the grains with which the grains get out of the system. We normalize that with the velocity of the bell, because we want to get rid of some fluctuations that might be on the velocity of the bell. And we found that independently of the initial packing fraction, we have that the velocity that the grains get out of the system is about the velocity imposed by the conveyor belt. So the initial packing fraction has no influence on the velocity on which the grains get out of the system. So as I said before, we have this expression for the flow rate. As I said before, it is proportional to the packing fraction. Velocity is not influenced by the packing fraction, as I showed before, and the rest of the things are kept constant. So what we see is that there are some variations on the flow rate. They have to be related directly to the packing fraction. So they're related. You can see the mouse here. Sorry. So they are directly related to the packing fraction. The variations. So we have proposed a model for the behavior of the packing fraction, and what we did was to make a balance of, in this region of interest where we are measuring the packing fraction, we make a balance of the grains, the number of grains that are getting in this zone and the number of grains that are getting out. So the increase of grains in this zone is related to a rate that is proportional to velocity. The velocity is higher, more grains enter in this zone, to the number of grains that are upstreams, which is related to the packing fraction upstream, which is about the packing fraction in the zone, and to the available space. The system it's highly packed in this zone, then there will be less things that may be allowed to enter this zone. And then the decrease is easier because it's only proportional to velocity. More things flow out of the system if the velocity is higher, and it depends on the local packing fraction. So if we take this in consideration, we obtain for the evolution of the packing fraction a kind of logistic equation for each value of the conveyor belt. And in this case, it has two parameters. One is the asymptotic value, which of course is found that it is a little bit less than the maximum that can be achieved. And we have this alpha value that introduces a time scale. So, as I said before, we can traduce this characteristic time scale to a characteristic length scale, considering the velocity of the belt. And so, for the packing fraction as a function of the displacement of the belt, we have a kind of a logistic solution of this kind with a characteristic length scale. In this case, all the curves, as I said before, they all collapse. The asymptotic value is about 0.8, and the characteristic length scale is 2.5 centimeters in this case. Then the other thing we wanted to understand was the evolution of especially the non-linear variation of the number of things flowing out of the system. As I said before, sorry, I can't find that here. As I said before, the flow rate is related to the packing fraction, and we know that the flow rate is related to the number of grains that are leaving out of the system in a time interval. So if we integrate that expression, we obtain a solution, a behavior like the one described here, which is the one there. We can see here that in the case of the number of things leaving the system as a function of time, here we have some experimental data for different initial conditions. We see the non-linear behavior for the ones with initial low packing fractions, and we see that in the case of the densest system, in this expression, because the initial packing fraction is close to the asymptotic value, all this term goes to zero, and we recover the linear behavior of n as a function of time, and therefore the constant flow rate. So I don't know how I am with time. It's okay, I will go quick. So what is the meaning of this characteristic length? We have proposed that this characteristic length is that the travel distance over which the system has to needs to reach the steady state. So as I said before, the grains are packing over when we have an initial low packing fraction. The system is getting packed against the downstream wall till it reaches the asymptotic value. So this is the length conveyor belt will have to travel to reach this steady state. So considering that, we have found that in our case, this length scale should go like this. Is proportional to the aperture, to the difference between the initial packing fraction and the asymptotic value. and a relation between the aperture and the width of the system. That is the width of the downstream wall. So we have found that this is this interpretation of this length scale is correct. Here in these black squares, we have what is obtained from the expression we have proposed, and in white circles we have the values obtained with the fitting of the experimental curves, and well, they are okay within the experimental errors. And moreover, we found that considering this expression, we have everything constant except the terms that in which we consider the initial packing fraction. So if we plot lambda as a function, if we plot lambda as a function of this term, which considers the initial packing fraction, we have effectively a linear relation. So in conclusion, we have seen the packing fraction variations do not have any influence on the velocity of the grains at the outlet, at least for these values of velocity we have studied. And then the Weber law still holds if we consider just a modification that the only variations are to be introduced in the term of the packing fractions. We will control then variations in the flow rate. So that's all.
You showed the curve of it was a capacity in terms of time, and that curve when they overlap the previous one, you have less curve. One can see, you can clearly see the exponential that you did, but you can also see like fluctuations.
Yes.
Those it corresponds to what?
Well, I don't
because
know.
They are very
Yeah. We see that there are some kind of fluctuations.
Yeah, and in the field they seem to be like longer periods at the beginning and then shorter ones toward the end.
Yes, when the values is reached. Yes, we haven't seen in detail. But yes, I have some questions.
Comment on the question of the colleague there. In fact, one is expected to find always for fractions of flow because of the presence of bars.
Yeah.
No, sure.
Compacting, this is of course a dynamic process. So
Sure. But
you're compacting, so you're expecting to have these fluctuations, and in fact, in the right to a steady state, you will still have fluctuations.
yeah, what I mean is that those fluctuations were very concentrated at a fixed frequency.
Yes.
It was very coherent.
Sure.
And that frequency is related to what, to which number in the income. How will you do to change that to something else? It's a no. I asked because out of curiosity.
For instance, the aperture. Change the aperture.
Yeah, different frequencies.
Yeah.
There's another point maybe related to that. The question of the friction composition of that, the friction between the conveyor belt and the grain, the particles.
Well, in the Weber rule, the friction is proven. I don't think it has to be. There are many systematic works I know. I have looked into it. At least it has been believed that the particle-particle friction is not that important for flow rate. But we have found that many things have been said and not all have been actually experimentally demonstrated. So I'm not sure about that. And the thinking here is actually that in a way, friction here on the grains with the belt is controlling the force that is done on the downstream wall. And actually there was this type of experiment that give us this insight that pressure was not controlling the flow rate, because in this type of experiment, while the system is getting discharged, we have less rain, so we have less force related to the friction on the downstream wall. So in this kind of experiment, the pressure is decreasing throughout the whole discharge, nevertheless, the flow rate remains constant. So this was our first result, which led us then to do some experiments in gravity drill systems, and we found that they're not, so that they're not actually related, even though both are more or less constant.
It would be interesting for this kind of experiment to do anisotropic friction between the direction of the belt. If you have like a belt like a
with
pattern,
different zones,
like a pattern with lines, and you have grains move more difficulty perpendicularly to the belts than the line.
I'm interested in this.
Thanks again.
Okay, thank you.
Okay, so we'll have a coffee break now. We'll be back at 11:20.
Okay. Lo dejo después, no saco porque voy a ver si. Porque si le saco el cable se me apaga. Total, igual ya no molesta. Y después el coffee break lo agarro.
Sí, a las 12.
Sí, es la última de la mañana.
Sí, la última.
¿Qué quieres chupar?
No, de nuevo esta, porque esta es mitad.
Puede ser tuyo.
¿Qué tal?
Ahí está.
Bueno.
¿Cuál es el...?
Claro, todo eso pasa en YouTube.
¿Cuál es el...? Varias personas. Gracias. Pero está bien, si quieres ponerla ahí.
Sí, bueno, gracias.
¿Alguien no tiene programa todavía? La clave de Wi-Fi está en el programa.
La vérité, c'est que j'ai plutôt le film.
Ojo, esta habla bastante bien.
ese PDF de vuelta.
Ah, dale, sí. De este no tengo sorpresas. En este no habrá sorpresas. No van a haber slides que no hay.
No, igual
Perdona,
de
perdona.
de dormir un par.
No hay problema.
No sé, igual no sé cómo lo reciben del otro lado.
Sí,
espero
es
que te
verdad.
venda bien.
Ah, no te avisa José Eduardo, acá no lo conectás.
No, a ver. Creo que entendí el mensaje.
Está muy bien.
cuando lo colgo.
Está muy bien.
La primera vez que lo hago sin mucha preparación.
Sí,
así
está
que,
bien.
bueno.
No, igual además incluso supongo que acá la tasa de transferencia no debe ser.
No sé, a ver. Tengo el YouTube. Aún estamos ahí.
No. ¿Ves?
Pero no sé si se escucha un sonido. Es que todo pasa por el pequeño micrófono de mi compu.
Sí, es verdad.
Claro. Entonces te mando un mail mañana para...
Sí,
arreglarlo
sí,
para-
sí, buenísimo. Sí, sí,
Sí,
sí.
intentar. Creo que lo que estoy haciendo tiene aplicaciones y muchas cosas. Y la gente pensamos que lo que hacemos es
Sí, obvio. No, pero sobre todo porque...
Y no conozco el territorio.
No, por eso. Para que te vengas, lo conozcas, pero además a estas charlas van muchos estudiantes. Entonces te puede interesar, seguro. A ver. Ah, no existe. No, se podría armar.
Tengo que ver cuántos pago ya.
Dale, sí, estaría
Se
bueno.
puede hacer un par de clases.
Sí.
Yo puedo dar clases, pero le tengo
Claro.
No me interesa.
No,
Pero
ya
las
sé.
clases veo que yo estoy
Sí,
haciendo,
eso sí.
lo hago gratis.
Claro.
Sí.
No, pero lo que se puede pensar es, ahora lo que estoy pensando es, no sé cómo es la estructura para un máster, una especie de máster, pero sí, por ejemplo, materias optativas que sean regulares, eso se podría hacer. Era un curso
Por gente que
experimental de,
está
claro, sí, eso está interesante. Y sinceramente hay pocas materias que digan algo de know-how experimental. Hay pocas. Están las de la carrera, las básicas, pero no estaría bueno.
Bueno, vas a ver que me fue más o menos de la experiencia esa.
¿Te fuiste un poco? ¿Te fuiste al numérico?
Casi. Ahora lo que hago es determinación de control asociado, experimental, turbulente,
Sí.
tiempo real, con programación genética.
Buenísimo.
Sí.
Pero es experimental porque decís, vos decís que es control, porque es control.
Porque mi contribución a este proyecto, donde estamos como 20,
Sí, claro.
es de hacer código.
Ah, está bien.
No es este.
¿Agarró un café? ¿Te traigo uno?
Ah, si puedes llevar el
Sí.
café.
No sabía si tomabas azúcar de edulcorante, si te traje una de acá o... Gracias.
Él es Lucas, el experto del
¿Cómo está?
hospital
¿Todo bien?
italiano. Ponemos en mi compu,
Sí.
por las dudas, la charla de él, que son unos videitos a continuación de mi charla.
Dale.
¿Dónde estás?
Está copiado.
Igual prefiero si me
Sí.
apuro, o si querés te dejo primero. El problema es que
Mirá.
sin la introducción no sé
Yo con que termina a las 12:10, llego. Y quiero llamar ahora a ver si realmente
Te tenés que ir.
van a hacer un operativo que no sé si yo tengo que formar parte. Viste que somos medio bomberos.
No, está todo bien.
Si no me necesitan, nada, tranquilo.
No, porque si no, el problema es si te dejarte hablar antes que yo, es que para que se interprete lo que vos decís.
¿Tienen en tiempos bien?
Sí, pasa que ahora a mí me toca
Yo largaba a las 12.
a las 12, si yo
Pasa que
hablo
vos-
15, así que entonces si no corto lo mío, pero ahí
Déjame que averigüe, a ver si capaz
A
no
ver.
necesitan. Yo te consigo.
por las dudas. No, si podés salir, si salís 12:20 estamos fenómenos.
Tiene de la...
Todavía no lo vi, ahora es medio lenta, pero va a venir.
Te copiar mi computadora.
¿Qué pasa? Está buscando.
Tiene una carpetilla llamada Gris.
Muy bien,
Ahí tiene un video.
muy bien. Esperemos que la lea. Si no, yo tengo lo que me mandaste por WhatsApp, lo habéis pegado por las dudas en la charla, pero digo, bueno, si ves.
Sí, son las imágenes. En realidad es un poco eso y
Además, sobre todo,
contarle
parece que cuentan
qué es lo que
cuál es el
hacemos
procedimiento
nosotros.
también para hacer eso y que, o sea,
Y un poco le puse el libro al final.
Sabes que estás al frente del canal.
bueno, pero se me ve el pelo.
Se te ve el pelo.
Bueno, ¿por qué no lo lee? A ver, podemos probar en el tuyo.
¿No lo ves?
A ver, podemos probar. Pero vos encima no tenés.
A ver,
¿Esto es PowerPoint de Office? Espera, cambiemos de Office.
No tengo Office. No tengo ninguna cosa que...
Nada de pago.
Office no tengo.
¿No te reconoce el pen? ¿No te lo toma?
No sé, no lo está viendo, no sé qué pasa. No puede ser alguna máquina, lo va a ver. Si no es la mía, sea otra. No hay.
Es raro. Tiene al lado. Que la foto USB.
Sí. Prueben la otra.
¿Te ha pasado que no te
No. ¿Ahí vio algo?
No vamos.
Y no me ve el pendrive de Lucas.
Bueno, Roberto Díaz.
Pendrive, si quieren pasar de pendrive a
Sí,
pendrive.
pero no.
Espero que no se haya quemado. Este venía
Sí.
bien. Hace muchos
Lo
años
tiene
que
que
lo
leer,
usamos.
lo tiene que leer alguna.
Es el tuyo.
Este es mío.
¡Ah!
Sí, sí.
Ay, no. A ver.
Ah, espera, yo te lo pongo.
Ahí va.
No. No. Hernández, el Lucas hay uno, pero es por
¿Lo ves?
agregué a mi Facebook.
There's a problem with his drive.
Estás en el-
Scan the drive now and fix it.
Oh.
Ahí va. lo
Ay,
tengo.
bien.
¿Cuál es?
Espera, ¿me lo copias en el mío? Uy.
No hay lugar.
¿No hay más? Bueno, copialo.
Saca este.
No.
Saca este.
La Viviana, que es la prima de mi viejo.
¿Cuál es?
Denise. La carpeta de Denise.
No.
Todo, copia todo por las dudas.
Tengo la
Controla. No era. Sí, bien mal. Ahora estoy pasando al mío y ahora lo meto.
Parece que se va a perder la opción.
Sí, pasa que lo que pasa es que para llegar al producto final que uno quiere, tener un costo de prueba de error no se sale dinero. Entonces, si vos tenés claro lo que querés, hermano, sale casi gratis. Porque uno no te puedes dar el lujo así, bueno, es lo más tenés que reunir, definir, ver la presentación claro lo que necesitas, porque tenés muchos materiales y a ustedes cambian. O sea,
pero sí, lo que es importante es que el material también eso sería
Estas son tus...
eso es difícil. La geometría sí, material no.
y
Es esto, ¿no,
a la
Lucas?
tráquea
Eh...
es difícil.
Ah, tenés unas cuantas. Voy a tener que achicar la mía.
No.
No, todo bien. ¿En serio? ¿Vos decís todo eso en 5 minutos? Qué grande, bueno, muy bien. Fenómeno. Y el video, a ver, para ver si anda, ¿es este que está acá? ¿Cómo se llama el paseo? Que nos hizo el favor.
Anonimizado.
¿Es anonimizado?
No se puede decir eso.
No, pensé que era el apellido, por eso me...
No, eso es otro. Tenemos medio entre anonimizado y medio el nombre ahí, pero igual.
Hay que hacerle un homenaje.
Sí, no, lo que hicimos. Escúchame, porque nosotros no hicimos el video de.
Ah, ¿no tenés el video de la nariz?
No, porque no hicimos dos tomografías, hicimos una sola.
Sí, más o menos.
Hicimos solamente la tomografía que iría con el paciente.
Sí, y eso lo tenés para mostrar.
Pero
Entonces muestro yo el videito que me pasaste vos por WhatsApp. Ese sí es.
yo me callé la no.
No, esto, cómo se llega de lo que se hace en la construcción, pues las diferentes herramientas puedes tener transparencia, esto que te vamos a hacer, estudio de simulación, fotografía, esto lo que son 3D, y bueno, yo lo que voy a mostrar es un caso donde mezclamos todo lo que es la variación con el método de impresión.
Bueno, buenísimo.
Esto es lo que tenemos.
Está bien. Entonces yo puedo, si me permitís, te mostrar
Sí.
esto. Que lo me pasaste por WhatsApp.
Bueno, sí. Dale, sí.
Nada, y no sé, si querés lo describís vos, qué sé yo.
No.
O sea, lo que estamos viendo ahí es la reconstrucción 3D. ¿Cuál es el
¿Vas a hablar en francés o vas a hablar en español?
No, voy a hablar probablemente en inglés, porque ahora veo que todos hablan en inglés, no sé.
Escribo en italiano.
No, ¿quién no habla francés?
¿Y en italiano quién no habla?
Bueno.
A mí tampoco. No, tampoco. No te creo mucho igual.
No, digamos, esa sí es la toma del trabajo que estamos haciendo, visto desde arriba, para poder hacer un 3D. Y sobre la adquisición de esto, me dejo hablar a vos y te doy el paso.
Bueno,
¿Está bien?
dale.
Buenísimo. Entonces ahí, plin plin. El tuyo lo dejo abierto en la primera.
Sí.
Estamos. Dejo abierto estas dos cosas también. Vamos y vamos a guardar. Listo. Bueno, fenómeno. Genial.
Así que.
Bueno, ¿quieres tomar café?
No, que.
¿Te hacen el café? Masito.
Sí.
Il y a quelqu'un qui
Oui.
m'a dit tout à l'heure qu'on n'entend pas bien derrière. Est-ce qu'on peut mettre un micro?
Il y a des micros. Il y a des micros.
Alors, il me dit qu'on entend
Tenemos tiempo.
Yes. Por esa voz así.
Así es.
Yo creo que por la forma, no sé.
No, sí, tampoco las cuestiones.
No.
Hay dos micrófonos.
Sí, claro, no estamos por atrás. No tomas nada. ¿Cómo viene la conexión? ¿Alguien se conectó
Sí,
para
bastante
ver
bien.
algo?
Hazle con celular,
Sí.
sale la conexión en YouTube. Creo que el sonido está.
Siempre se conecta.
No, una cosa que dice más o menos como ya tiene logra hacerlo.
Ok. Claro, porque es complicado.
No, pasa por la micrófono.
¿Qué pasa? Ok.
Esta la para probar.
Bien.
Bien, por suerte te vi ahí, esa que estaba para probar. Esta era para probar. Por esta es la otra.
Claro. Sí, es mucho y además la tarjeta se mueve. Se mueve en la dirección.
Sí, puede pasar por alrededor de esta de la
Sí, es lo que le acabo de decir. El mínimo.
So we are using the microphone now.
Hola, hola. ¿Quiero gritar? ¿No te sale? No, pero puedo estar haciendo un show. ¿Crees que lo tenés que volver a contar?
Sí, dale.
Usa esta prueba. Porque si así, sí, claro, el USB te dice si quieres escuchar alimentado. Tampoco sabe. Ah, ¿está prendido o está apagado? Ah, puede ser. Por ahí se puso en stand-by. Ahí vuelve. Overheating. Ah, no, es filtro. Okay.
So we're back, and you already know Pablo already, so we will be giving another talk about supershear array waves something.
Thanks. So yes, I will talk now about a different system. This is a soft interface. So this is a work that's been published in PRL, but we have new results now, and it's an ongoing research. thematic for our group. So everybody knows that in solids, in elastic solids, we have Rayleigh studies on elastic surface waves. So those have been experimentally verified, numerous waves. And the new thing is that there's been a long-lasting controversy on the existence of super shear Rayleigh waves. You know that you have Rayleigh waves, standard Rayleigh waves, and those travel at a maximum speed. But there's been two very known reports, both published in Science, and there's been a lot more in specific journals about it, as if in seismic events there were propagation of a wave much faster than it is expected. Okay, much faster than Rayleigh waves, and it's been very difficult to model this because all you have is seismic observations, and due to the heterogeneity of the soils, is often very difficult to model what you have and to tell one kind of wave from the other. So what we did was we took a foam as a viscoelastic model of our soil, and we used the technique that I've shown you before to study the waves traveling at that soft interface. So very quickly, you can think of a liquid foam, such as that one, the one you shake with, as consisting of a concentrated dispersion of gas bubbles in a continuous liquid phase. Okay? And so what we are going to do is that we are going to model some sort of excitation, but it has to be very sudden, it has to be of very high injected power in order to mimic a seismic event. So what we will do is something very easy to understand. We are going to throw some sort of a bullet onto our foam. Okay, so we depose our foam, we shape the surface so it is flat, and we let it fall, or later on we drop into that at a fixed velocity and controlled fixed velocity this ball, and we are going to measure the waves emitted by this phenomenon, by this impact. Okay, so it's quite simple. You see there. Our system, so you get to see the true projector, the high-speed camera, the system there, okay, and what is imaged by the camera. And you see there, maybe you saw it already, there's the impact of our little ball, and you see that the pattern deforms a little, just a little. It's almost imperceptible to the eye, but this is what you get when you calculate the height mass by French projection profitometry. This is what you get. The color codes the height, the local height, okay? And this scale is in microseconds, and this was filmed at 1,000 frames per second. So this is typically what you get. And what is interesting is that you get there, what you get in red, obviously is the shape of the ball, but what is interesting is the waves that are emitted from there. So I show you there 3 snapshots in time of what is emitted by the impact. There you go. And the final state there. Okay. So based on this, and due to the axial symmetry, okay, you can just take a radial cut and then angularly average it, and you get this spatiotemporal plots in which you can see for 2 different regimes. For example, for an impact velocity of 1.85, 82, or 5.53, you get 2 very different responses. You get this bulge here that corresponds to something that is generated, to a wave, and here is, you can almost see it, okay? And this is for different radii of the ball, okay? And if you plot the height, if you will, this is the depth to which the ball goes into the foam, then you get that for low velocities, you get up to there, 0.5 millimeters. But if you increase the velocity, you get up to this depth, and later on, if you increase further the velocity, it goes down. So the ball does not penetrate the foam that far. Okay, so you have like a peak and 2 behaviors. Okay, near that peak, and that is what we are trying to model. So we can perform a Fourier analysis of this. So we have the H there is the height field. Okay, so we Fourier transform that, and we have an amplitude and a phase. And from that amplitude, we can make a model such as this, which has been published before by Carcione, for example. It's classic. and you get also some measure of the phase velocity for the waves, and you get this. Okay. These are experimental results with the error bars, and you get in black and in red are the two different regimes. Okay, less than 2.5 meters per second, or more than 4 meters per second. And you have this this blue board is a classical model. We are not trying to model it; it's just there for comparison. But you see that for the low velocity, the model works pretty well. And this is well known in the literature. But we get this second way of working of response for the system, and the same here. Okay, this is just for the phase velocity, and this is for the typical length of our wave. So we have these two different regimes, and we are trying to model them, to explain them. So if you think of a foam like a viscoelastic, then you have the typical bulk waves, like the P wave for compression, the S wave for shear, and you have also surface waves. Okay, just like in water, you have the equivalent of that, and this is the Rayleigh wave. Okay, what is typically called the shear surface wave. And if you order them by velocity, you get the fastest are the V wave, the compressional ones, the velocities are not there, and you get the slowest ones, which are the surface waves. So, in terms of phase velocity, we have this, okay, in the model that I've already shown, and we have a difference from around 200 hertz. We have this discrepancy between the two. So there's two possible reasons one can think of for this difference, and one is that there is a nonlinear increase in the elastic models that changes the shear and the Rayleigh waves, their characteristics, or there is a superposition of a secondary faster wave, kind of wave. That's already been proposed in the seismic community in those science papers that I've shown before, and that is the path that we are going to explore. If we further increase, so we exaggerate and we further increase the impact speed, for example, for around 18 meters per second, we get this. And we get this first wave and this much marked secondary wave there. And those correspond to the two peaks that you see there at two different locations. This is a plot of 8 versus 9 for this spatial temporal plot. So you see that, as I said, there are two bumps which are noticeable there, and for distances less than 3D, which is the diameter of the wall, the first bump predominates, but so you can do a monomodal Fourier analysis of this. But the question is, what is the nature of this second faster wave that you observe? So the question is it an elastic-like wave or is it a liquid-like wave? So we have this prediction that we can get from the ratio of the surface strains induced by liquid surface waves versus elastic surface waves, yes. And this is the parameter that controls that balance. And if we calculate this, it gives us something less than 0.02. So this discards the liquid-like behavior. So this second kind of surface elastic wave can only be Rayleigh waves, but the problem with Rayleigh waves is that you have a limit for their propagation, and these waves travel much faster. So there is something very interesting in reading the original Rayleigh paper, in which he discards as regarding not physical the solutions with K complex. Okay, so there is a branch of solutions that he discarded because basically he thought they would never be observed. They were only mathematical curiosities, and they were not physically meaningful. So we went down this path, checking for these complex solutions, and this is what we term super shear Rayleigh waves. Okay, so these are elastic surface waves which have to propagate much faster than the typical ones, and they are transfer polarized. That is another anomaly. Okay, so these predictions we already discussed by Cazione, and if we do that, if we put that into a model, we get the Rayleigh waves. And if we take into account the complex solutions that I talked before, we get this. Okay? So this second branch is very well explained within the experimental error as accounting them to super shear waves. Okay? So the system behaves for low frequencies, the response is just Rayleigh waves, and for high frequencies, the response is super shear Rayleigh waves. And there is some sort of change here that one might think of bifurcation. So we still need to explore how this bifurcation takes place, but it is there and it changes from Rayleigh waves to these new supershear Rayleigh waves. So this is the first experimental evidence of the presence of these supershear Rayleigh waves, and it's visible for impact velocities which are faster than measured shear wave, and that corresponds to a frequency of 200 Hz. If one does not need to speak in terms of velocity, if you want just to know how your phone responds in terms of frequency, well, your phone responds as it should, as you already know, with Rayleigh waves for frequencies less than 200 Hz, but if you agitate your phone with higher frequencies, it will still respond, but it will change and it will emit supershear Rayleigh waves. So within foam science, this has been a very pioneering study in surface waves in the liquid form. It's the first time that anybody measures the deformation of the surface. We've shown that there is a coexistence of these two kinds of surface waves. They both exist, and you can tell them apart. The only quasi-elastic Rayleigh waves are observed, but after a slow impact, and when you have a faster impact, then you get super shear. Beyond foams, one can think of this as explaining, in other materials, explaining what's been observed in geophysical science. And these super shear seismic events that have been reported might probably be that manifestation. And this could be very interesting to check within water or oil field soils, because foam is a very good model of highly concentrated, water concentrated soil. So this can be of interest to the community also and for applications. So that's it for me. If you have questions, I'll be glad to answer them. Yeah. Sorry? Ah, yeah, okay. So, yeah, it's an evanescent. It's an evanescent, but it's low. It's very low evanescent. That's the point. So it's positive. Yeah, absolutely. But the thing is that when he described the complex solutions, those complex solutions were not imaginary solutions. Had a real part also. So the complex part was very slow, okay, in evanescence. So you still get to see them in the lab, and probably in seismic also. But what is funny is that the real part of that complex K is very important, much more important than the Rayleigh waves.
All these, I mean, for fracture mechanics, the quark, the related waves, the speed of the quark.
Yes, that is what is being proposed in these science papers.
Okay, so the speed of the quark can be higher than the
that's the point. That's what's being reported. Here, I mean, in those two science papers, those are more like general community oriented. But if you go to geophysical research papers, those say exactly that.
Okay, so you don't need viscosity to observe the...
No, not in principle.
That night I was thinking of when you think of this shear dipping fluids.
Yeah.
Like a Mycena.
Ah, yeah, but that goes into beyond, yeah. But that means it's heavier to model. Thanks.
So we'll switch the next two talks. So we have Denise Yamarella, who will be speaking first, and then, so that's the talk that was noted for 12. And we have Florian Suarez's talk after that. So Denise will be talking about both extremes in biomimetic local depths.
Hi,
We thank Florian for letting the order of the talk. The reason is that I'm not alone. I will make an introduction of what we are doing concerning floater jets. And we have with us Luca Vitaco, who comes from the Hospital Italiano and who works in CONICET at CDO, who has come to communicate some a project that we have undertaken quite recently. And so I'm going to introduce the subject. The talk is titled Vortex Tubes Environment Floater Jets. It is work that involves myself from UNICEF, Pierre Audier, who was a postdoctoral during a year at the LFD, at the Facultad de Ingeniería de la Universidad de Buenos Aires, in the lab that is directed by Jornadas. And then there is Luca Vitaco, whom I have already introduced. The subject of my talk is the voice. We have already done a meeting, a voice meeting in the same place. Something's happened with the microphone now. So, for long years we have been describing the physics of the jet, the air jet that exits the glottis from what we observe frontally, so in the coordinate plane, in the graph, the plot that you are seeing here. But this is only true, this description of the fluid in the foundation system is only true, it's only valid, if the flow stays more or less the same along the glottis, which is a long orifice. And the talk is going to be about that. This is a short didactic video that was produced by the University of Lyon. I like it very much because it rapidly gives the context of the problem with which we are working with. So what you are seeing is the lines, and we are soon going to see how the muscles adjust their position to get the glottis in the configuration that allows for phonation to produce a sound. That's the right configuration, so we have this long orifice, which is the glottis, and then we are going to see an animation of the vocal cords, which are the two membranes that you can see here, and you find the air pressing against these vocal cords, which will start oscillating through a balance of energy, which is achieved through the interaction between the structures, the vocal cords, and the air. That's the plane that is described in all the models. But that's the vision, the image that interests us, because we are interested in the fact that the glottis is not just a hole, but a long orifice. And jets exited from long orifices have particular properties. This is a long-standing collaboration. We've been working on the subject for a long time. It's mainly a collaboration between the INSEE and the NFD. And I comment on this result because it was the first work that allowed us to undertake the work that I'm going to talk about now. This was a pioneer work. We achieved in 2012 the first three-dimensional reconstruction of the flow exiting a model of the glottis, an artificial model of the glottis, which is made of two latex lobes filled with water that oscillates in the way that you can see in the video. So with this scheme and using stereo particle image velocimetry, we performed the first three-dimensional reconstruction of the flow in the region, in the volume that is close to the orifice, to the long orifice formed by the glottis. So the long orifice is in this direction, and this is a glottal cycle. This oscillation is typically around 100 Hz. And the most remarkable phenomenon that one can see in this region is that the jet is far from being two-dimensional, there is a very strong three-dimensional phenomenon which is common to all elongated jets or slender jets, which is called axis switching. You see that the flow field is oriented along the length of the slot, and the orientation is inverse a few millimeters downstream. So this is the first three outstanding three-dimensional characteristics that our experiment confirmed, and we have recently incorporated in simple models of vocal oscillation that can be used to predict to produce voice signals. We have incorporated this to simple models under using the concept of a relaxation distance that the jet has to develop before it can be really approximated by a simple flow line, as it was in the models dating from the 1970s. A more recent experiment in which we reduced the complexity of the model is an experiment in which the glottis is modeled by a static geometry composed of two facing cylinders defining an elongated rectangular orifice, and the first thing we did with this simple model was study the properties, again, in this configuration with a continuous jet instead of a conflicting jet, and our surprise was that when we could access the vicinity, the close vicinity of the jet exit, we did not only found this property of the jet direction called axis switching, but we also found that the jet was split. The core of the jet was split into two jets. So we find a bifurcation of the jet in the close vicinity of the glottis. There, where everybody believed that the flow was just planar. So these extra-planar phenomena are important because, in the first place, they were absolutely not considered. And in the second place, we know, and I cannot develop that because I don't have the time, that we can use them in simple models to predict qualitatively different results in the voice signal, in the acoustic signal. This particularity of elongated jets related to the fact that they can become bifurcated is not completely new. We have visualizations dating from 89, where Hussain and Hussain observed an elongated jet that first underwent axis switching and then split it into two jets. A more recent article, which is from 2014, makes a summary of a number of papers dealing with elongated jets, not in the field of voice production, naturally jets, elongated jets, non-circular jets are a general subject of fluid dynamics, speak of a number of phenomena in which what they find in the velocity field, because they do not generally recover the full field flow, they recover what they call saddleback profiles. These saddleback profiles are nothing but the bifurcation in the close vicinity of an elongated jet, in this case a rectangular jet, which you are seeing here. But even if it is observed, and in numerous experimental essays, that when a jet is elongated, it bifurcates when the aspect ratio is higher than more or less 5, nobody knows why. And nobody presents a mechanism allowing to explain what is really happening. And to explain what is really happening, what you have to look at is vorticity. And you have to look at what's happening with vorticity in time. So you need to be resolved in time, which is not necessarily easy, experimentally speaking, when you're trying to describe a volume, a flow in a volume. We had, in the image I showed you before, already the mean fields, and we see effectively that the elongated jets present a property, which is that next to the, close to the exit, you see two vorticity tubes that are formed, immediately formed. What happens for two infinite vorticity tubes? What if they are contrarotative and they are close together? This is a simulation made at Lindsay by Van der Waal and Fossil.
And we find that the coexistence of these two tubes produce the development of an instability which defaults the tubes and which can promote reconnection phenomena. So, if we want to understand what's happening, we have to access the dynamics of the vorticity in our problem. But how to access, how to be able to resolve our problem in time when we are reconstructing a volume through a sweeping of a number of places, we have to phase lock if we want to recover the vorticity in time. To do this, we have implemented a methodology that uses plasma actuators. The laboratory of fluorodynamics at LIA worked for a long time with plasma actuators. They have the expertise on the field. It is a very simple technique, and in the case we are dealing with, it allows us to inject a small perturbation that allows to do the phase locking that we need to be resolved in time. So we have reconstructed two half glottises that we can place together in this way, and this is very practical to be able to correctly position the electrodes that allow us to inject the ionic wing. This injection of ionic wing will be synchronized with what we know is the preferred mode of the jet, so the frequency of instability that is most frequent, and in this way we can obtain the following result. In the first place, when we reconstruct the 3D field with a mean flow, we recover the bifurcation. But now, thanks to the plasma actuator methodology, we can also recover how the vorticity field is formed at the closed exit of the glottis. So this is our glottis, the glottis is placed in this direction, and we see pairs of contrarrotative vorticity tubes that exit periodically the rectangular section that we are examining. Now, if we look at these structures in the plane, the transverse plane, we'll see that as they advance, they deform, and they finally deform, forming an H shape, which is consistent with this saddleback profile, saddleback velocity profiles that I showed you some moments ago. So these measures allow us to now undertake an analysis at the same time that we do when we analyze the crow instability. When we have, this is well known, when we have two infinite length vorticity tubes of ratio A and separated by a distance p, there is a diagram. The diagram was published in 2011 of the crow instability, which tells us which wavelengths are developed. There is a region that is stable, a region that is unstable, and we know around which values we find the maximum growth for this instability. But in our case, the vorticity tubes are not infinitely long. They have a finite length related to the finite length of the orifice. This introduces an additional supplementary condition which, combined with the diagram of the crow instability, allows us to explain what's happening and to predict whether a jet that has a certain aspect ratio, a certain separation between the tubes and a certain size of the tubes, will bifurcate or not. So, thanks to the reconstruction of the vorticity field in the vicinity of the exit, we have the zero mode, which would correspond to the absence of a bifurcation, and we have the first mode, which corresponds to the H shape in the vorticity ring, and which is placed in the diagram close to the maximum growth rate of the instability, which allows us to explain why our jet is bifurcating. This is the first time that a mechanism is proposed to account for this experimental phenomenon that was observed for more than 40 years ago. And that's not all. I mentioned before that in the literature concerning jets, it had been mentioned that bifurcation occurred if the aspect ratio was higher than 5. Why 5? Looking at this diagram, if we look at the limit of validity of the diagram, and if we assimilate the separation, the limit separation between the tubes with the width of the orifice, we can find effectively that in order to have the instability developing, we must be at an aspect ratio of about 4.7, so that's near 5. So in this way, using the diagram and proposing this mechanism to account for the bifurcation, we can not only predict why our jet is bifurcating, but also why, in general, jets of aspect ratio larger than 5 bifurcate. The only problem with this, to apply to the problem that we were discussing, which was the glottis, is that some publications mention that this phenomenon is very sensitive to the geometrical details of the nozzle. In general, we talk about nozzles. Our nozzle is the glottis. But how do we know that this is really happening in real formation? Because we are working with a model, with a very schematic model made of 2 cylinders. How do we know that this is really happening when we talk, when we produce voice? And this is the project in which Lucas Ritaco is involved. In order to answer this question, we need to have access to the 3-dimensional reconstruction of the airways of a human being that's producing a sound. And he has helped us, and he will tell you how, and with a team that is that has an experience and a trajectory in this field. And these are the first images which we hope will allow us to make a 3D impression, a 3D printing of the lines that will allow us to have a model which is no longer schematic and with a geometry that exactly corresponds to a human being that's producing a vocalic sound. This was done with a patient with a tomography, and the patient was asked to make a vocalic sound during the study. So I will let him introduce his team, and I mentioned also that Luca Ritaco is integrating one of the CAPSI projects that have been proposed and that also make part of the French-Argentine collaboration projects. I will take him.
Thank you so much to you for inviting me, and just only a few words on computer aid surgery. Great presentation, even I'm nothing. It's wonderful presentation for us. That new in
No tengo.
Okay. Computer aid surgery is a new specialty of the medicine. We create a casting in the italiano, the next one. The objective of the gas unit is simply for designer and engineers, and I am the only medical doctor that I am in the group, this one. The unit responds not only to orthopedics, the place that I work is called Cineos for orthopedic, but now we are working with another specialty, neurosurgery, maxillary surgery, and water surgery of the body, the next one. One of the tools that we use is the Virtual platform. The Virtual platform integrates the tomographies, the MRI, and a lot of kind of images in the same scenario in order to create an interactive tool, as like this picture, for example, it's a tumor, the wing, it's a pelvis tumor, and the idea, for example, was cut with the red plane that you can see, and this kind of tool it changes all the paradigms that we have. now in a lot of centers of the world, just only plan using two-dimensional images, and the idea now is to include this kind of scenario in order to take some detailed aspect details using this kind of planning, for example. And now we are talking of, for example, uniplanar, biplanar, and multiplanar. That it's pretty new. It's very new for us to decide of using these tools. The next one. Recently, we are applying not only image rigid, but we use this kind of image, and then we change the pixel of the digital image for a binary value. This is a process that is called segmentation. The idea is segmentate slide by slide, and then refine this model in order to get this another model that it's a three-dimensional model, because the project requires just only taking account what's happened of this area. So another tool that we have, this is programmatic planning using virtual scenario, but we use navigation that is for surgery and 3D printers. The idea of this project is print this model in order to create the geometrical model quite similar to the human, and also for future perhaps include another properties of the material in order to create a reality sample. And then prove this kind of samples in virtual scenario in order to use filling elements analysis according to the fluids in this area. The next one. Okay, and this is the planning that allow us interactive with the 3D images and response to some complex technical aspects in the surgery. And in the case of the 3D printers, we have a lot of material. Not only we have plastics and we have powder. And the idea of our model is to print in PLA plastic model and adhere this kind of model respect the real geometry using this rigid and plastic model. Next one.
Sí, ya te one more minute. Te recordito el tiempo.
Okay. The next one, it's a model that we. Next one. It's a temporal model that we use to explain and train. It's a training method that we use in the hospital when we have some surgery that the tumor are located in some area. And the next one. This is, for example, a trajectory that was planned using virtual scenario. This was a clarified, and then we used the same. We used the virtual model printed in order to apply the surgery, and the final situation that was applied in the print model was in blue, and in the patient was in red. The next one. It's a video that shows you.
We are sorry to take a few more minutes, but it was not sure whether he would be able to come or not, and it is nice that he has been able to. The video doesn't work.
Okay.
It's fine. No, what?
Okay. Okay. This is the kind of study that we are doing in the class unit that allow us to compare preoperative planning and after situation when the surgery was executed in the real situation. And this is our last production of that it's a book that integrates the next one more than 10 nationalities. And I think that's in the next months is going to be great. So, okay.
Thank you.
Sorry for rushing, but we
Yeah,
are
maybe we want to skip questions and people want to come afterwards. And
yeah, while Florian sets up, maybe one question. Okay, so questions later. So next talk is the previous talk by Florian Duarte. We'll be talking about experimental investigation and the flow through two-phase cavities.
Hello, thank you very much. My name is Florian Türke. I work with Michel Martana in Camarela, Buenos Aires, and with the Pasteur in France in a so-called co-tutor in the framework of LIA on my PhD. And the talk I will give today is called Experimental Investigation of the Flow of Two-Phasing Cavities that I started doing experiments this summer or this winter, actually in France, and I will give just a short an overview over those experiments and what we plan to do with the results. The outline of the talk will be the following. The two-phasing cavities we call the double cavity. I will explain what it is and where it comes from. I will show the experimental setup and give a summary of the cases under investigation. Then I will show the experimental results, the PIV, the particle initial symmetry, and the LED, laser double symmetry results, and define the flow regimes in the double cavity. And then I will finish by an outlook and a summary. The double cavity is this geometry. We have two phasing cavities at a distance of d that we vary between 5 millimeters and 15 millimeters. We have the flow coming in from the left and leading to the right. We vary the flow velocity between 1 meter per second and 4 meters per second. And the cavity length is kept constant, and the cavity height is also kept constant. And the ratio between length and height is equal to. Where the double cavity comes from is actually very nicely explained by Denise. Was just the previous talk. We took the geometry that is formed by the vocal cords and the false vocal cords from Denise's project, and take an abstract form of that geometry formed by the real and false vocal cords that form this double cavity, and investigate the aerodynamical behavior of it. Well, the wind tunnel in MC in Paris has the following shape. It's an open wind tunnel. The air is blown in by a motor into a settling chamber, and then is blown through the test section where we see the double cavity here. And we use the LED device and a laser and a camera, which is then used to do PIV measurements. And those two methods are synchronized by a synchronization box and then processed in the computer. The double cavity generally has the following shape. This is just a schematic view. The flow enters from the left, and then laser is shown into the flow. The double cavity is made of plexiglass, and on the side there's glass, so the laser can nicely be shown through. And the camera is kind of takes pictures from above. And now the PIV measurements, we take two pictures very close to each other, then they are correlated, and we can compute the displacement, and from there, knowing the time difference, we compute the velocity field. And this is how the double cavity looks like in reality. We have this inflow channel so that we have a nice, well-defined velocity profile that enters into the double cavity. that is just this part here, and then an outflow region that minimizes the turbulent effects on the cavity. Well, in the experiment, this looks like this. So this is the laser shown at 15 Hertz into the double cavity. You can actually see anything, but this is just to see how this experiment looks like. And then when we visualize it, so we take now the camera from the top, and then it looks like this. So this is now the transient, just the beginning, so you can actually see something. Now the PRB particles come into the flow, into the double cavity, and I don't know if the light is strong enough, but you see that there's this recirculation region, and this is for a distance of 5 millimeters. This is the closest distance, and very low velocity, actually in a stationary regime, so that we can actually see something. Otherwise, when it gets too fast, the particles are distributed too fast, and you can't really see anything from just by the naked eye. Here, this is a summary of the 148 experiments we did. We varied the distance between 5 millimeters and 50 millimeters and did a 9th case, that is a single cavity, which serves as a reference case for our study. Then the velocities are varied between about 1 meter per second and 4, as I said before, and yeah, just a short overview. The first thing we were interested in is whether the spectra we find using the LDE technique inside the cavity, if it's global or local. So we took different points in the double cavity and found that for points 1 through 6 in this region, we find all the same amplified frequency peaks. That for that reason, we say that the shear area spectrum of the double cavity is global. We see in the cavity entrance we have no frequency peaks. That is as expected from an incoming boundary layer, a gaseous boundary layer. And inside the cavities, the intercavitary flow has a very high noise or high low frequency level because of the recirculation region. That's why the shear area peaks are covered by this low frequency content. So in this region we have the same spectrum no matter where we measure, and from now on I will just measure the spectrum in point 1 because it's the most amplified. We see nicely amplified peaks and not much noise in the background. So here is a summary of the information we obtained by those two techniques we combined. Here we see the double cavity with the mean flow field. The PIV system is not time resolved, so we get only mean profiles. And when we slice the double cavity, we get velocity fields in every slice that are plotted on the right. And then from the LDB probe points indicated here by the red and green point, we obtain the spectra. Because the LDB is highly time resolved, we recorded about 1000 Hertz, and we get those spectra. Here we see the power spectral density, normalized power spectral density as a function of the velocity and the Struhel number, and in a 3D plot. Here in the middle, the same plot just without the velocity axis, and here the same plot just with a logarithmic axis for the power spectral density. So this is the information we can obtain by the two techniques. And now the first thing we did is we took the simple cavity because it's a well-studied geometry in fluid mechanics over the past decades, and we could compare it to results by in other works in literature, and we obtained as other works in literature the two shear layer peaks, Struhel equal 1 and Struhel equal 1.4, which is commonly observed. So we validate our results with this, and now we see what happens once we bring the two. We put another cavity in front of this cavity and bring the two tap cavities closer together. So the first distance is a distance d equal 50, which is the d equal at the length of the cavity. And we see that the spectra look quite similar. So we have two well-defined peaks that are separate from each other, but in the double cavity case at a very large distance, already the second peak is more amplified. So now we bring the two cavities closer together, and what happens? That is, the second peak gets more and more amplified. So here we have the d equal 30, d equal 20. But still the two peaks are nicely separated, and slim peaks at the same Stoll numbers 1 and 1.4. So once we get now closer, that is at d equal 15, the two peaks grow together and will form sort of one big peak. And at d equal 10, even the Stoll number, the peak at Stoll number 1 disappears, and only one big peak at Stoll number 1.4, 1.5 appears. So there's the physics in the double cavity changed quite tremendously at those intermediate distances. And once we get really close, that is 5 millimeters, that is the video I showed you before. There now the physics change quite tremendously, because now we record a lot from the intercavitary flow. So all the low frequency content comes from the recirculation region inside the cavity. And we see, once we make a zoom, we see there's still this shear layer peak, but it's not anymore at Stoll number 1, it moves to higher Stoll numbers. So as a summary, for large D, the double cavity spectra is really similar to the single cavity spectra, and for smaller D, the spectra become very different. So plotting this now for one given velocity, u equal 2.23, for all the different cavity distances from 5 to the single cavity, we see in this region for d equal 25 to the single cavity, the spectra look very similar. So this is why I call this the single cavity regime. And once we get closer, we get to a transitional regime, and finally the physics change quite tremendously, and they become a double cavity regime where the peaks become broadband and move to higher Stoll numbers. So the next thing I want to talk about is the inflow velocity profiles. We recorded the entrance of the double cavity. We use that in order to calculate the momentum thickness, which is used as a length scale throughout many analyses we think of carrying out later on. So we recorded those velocity profiles, mean velocity profiles of the entrance, and then we compute the integral length scale, the momentum thickness, by fitting a Blasius boundary layer profile to the experimental points. Here we see the experimental points in red and green using F-min search fitting, nonlinear fitting function of MATLAB. And we fit all the profiles to the Blasius boundary layer profile and compute that way the momentum thickness. Here we see the momentum thickness as a function of the velocity, and another really useful quantity of the single cavity and also the double cavity, that is the length over the momentum thickness data as a function of the velocity. So now we obtained all this experimental data, and we at this point now we're starting to want to use it and want to apply it. And last year we carried out a linear stability analysis in a finite domain. That's a theoretical work for the simple cavity, for the single open cavity. There we obtained a mode spectrum from a linear spatial temporal linear stability analysis in an infinite domain, and then we conditioned this mode spectrum by the Kulikovsky condition that takes into account reflection of stability waves, and obtained that way a discretized frequency axis that compared with discretized frequencies that compared well with the shear layer modes of the single cavity. And now, since we have all the experimental results for the double cavity, we want to apply this analysis to the to the double cavity. And this is what we're currently working on. So first thing is obviously for this linear stability analysis, we take out the base profile of the single cavity, put in a base profile of the double cavity, and and then we will run the analysis. This is just from here now until the end of the year. Well, this is already everything I want to leave you with. Here's a summary. We carried out an extensive experimental study of with a wide range of velocities and cavity distances of the double cavity. We recorded mean velocity profiles and shear layer spectra with the PIV and LDV technique, and used the Blasius boundary layer profile to compute the momentum thickness and defined different double cavity regimes in depending on the shear layer spectrum of the double cavity. For now, the outlook is the application of the linear stability analysis in the finite domain, SAFD, developed for the single cavity to the double cavity. Well, thank you very much.
What is the definition of the Struan number? What is the length scale in the Struan number?
I used the cavity distance, the cavity length. This is F times L. The length scale I use the cavity. This is usually done in the single cavity. For the first shot, I usually use the same length scale, same scalings as in the single cavity. You can also use different length scale as the momentum thickness. I have to see what I will do again. But
on the flow, does that destabilize over this length? With the jet and the clip, you don't have any instabilities in the.
Yes, the shear layer instability. But we have the amplified frequencies. There's a lot of instabilities. That's why
you have a broad distribution of frequency because of this.
You mean in the very small? I think for the but there was still this is just ongoing work. But there's two things that are happening. First, the draw point when the cavities are really close together, we record a lot from the intercavitary flow. So this is not only shear layer, and on top of that, if you have a jet, then the oscillation of the jet is also quite low frequency compared with the high frequency shear layer spectrum. So we have a lot of low frequency because once we bring the two cavities really close together, the physics change. For one reason that the cavities are really close together, they interact. For the other reason is that the incoming velocity profile changes from a double Blasius profile to a jet profile, to a parabolic profile, which changes quite tremendously the physics. This is more a jet than a double cavity.
Question? Maybe you said about the outlook, but about the connection with the motivation. Thought about to go back to the cavity end, the cavity. Are there some sort of measurements that for these changes in spectrum that you could expect to measure?
I haven't thought too much about that yet, but that's something we need to do. We want to do.
You're not planning simulations because those simulations have a cavity which is quite shallow, and the cavity you find the growth is the total geometry is quite deep. But there are acoustical features that are not welcome when you approach what is called the force focal force, really.
So it is expected to find particular phenomena there. An example is the singing format. It is a phenomenon known by singers and professional singers in magnitude, and it's probably connected with the fact that the two cavities are interacting when you approach these focal forces. It's something that we do not in normal formations not done. But this is to be done, and this is to be simulated probably at ellipse it will get the simulation running quite soon.
More questions? Well, then I think we're done for the poster session now. Thanks again. So we have poster session up to 1, and then we come back up to